All right, part 5. Can do another example. In this example, we have w double prime of t minus 2 w prime of t plus 5 w of t equals negative 8 e to the pi minus t. And our initial conditions are w of pi equals 2 and w prime of pi equals 12. So the first thing we see here is that t0 is equal to pi. It's not equal to 0. And I said earlier that if it's not equal to 0, then we cannot directly use the method that we've been using. So we need to figure something else out. We need to adapt to this situation. So first let me say we need t0 equals 0 to use the Laplace transform method. So the way that we're going to accommodate this is we're going to make a substitution. So we're going to substitute a new function, y of t, and we'll define y of t to be w of t plus pi. That way y of 0 is going to correspond to w of pi. And that's going to convert our example here into one where we can do what we were doing before. Now, if that's my substitution, I need to figure out what y prime is. Well, we just need the chain rule. So we'd have w prime of t plus pi times the derivative d dt of the inside, but that's just 1. And then same thing for y double prime. It's going to be w double prime of t plus pi times 1. And so if we do that, then we can look at y double prime minus 2y prime plus 5y. And what's that going to equal? Well, it equals the same thing, but with w's and with a t plus pi. So I guess I could write it like this. I could say that's equal to w double prime of t plus pi minus 2 times w prime of t plus pi plus 5 times w of t plus pi. And what's that equal to? Well, go back to the original example, or the original differential equation in the example, and what you're looking at there on that last line, you're looking at the left-hand side where we've plugged in t plus pi. So that's exactly equal to the right-hand side where we plug in t plus pi. So it's negative 8 e to the pi minus the quantity t plus pi, which then simplifies to negative 8 e to the, well, you got pi minus pi cancels, e to the negative t. And then for our initial conditions, y of 0 is the same thing as w of pi, and that's equal to 2. And y prime of 0 is equal to w prime of pi, and we were given that that's equal to 12. So we've converted the given initial value problem where t0 was pi into a new initial value problem where t0 is 0. And we just have to solve that. Well, we already solved this exact example. So we can just write down the solution from before. The solution from before was y of t equals negative e to the negative t plus 3e to the t cosine 2t plus 4e to the t sine of 2t. So that's the solution to the new differential equation that we made. And then to finish it off, we've got to come back and convert it back to w. So our substitution that we made was this one right here, y of t equal to w of t plus pi. And if we turn that around, we can say that w of t is equal to y of t minus pi. And we can use that to write down the function w. So w of t, what we have to do is just simply take the expression for y of t, and everywhere you see a t, put a t minus pi. So I have negative e to the negative t plus pi plus 3e to the t minus pi times the cosine of 2 times t minus pi plus 4e to the t minus pi times the sine of 2 times t minus pi. And we can simplify that a little bit. Keep this as it is. And all this, keep that as it is. But here what do I have inside the cosine? If I multiply that out, I have 2t minus 2 pi. And of course, if we subtract 2 pi from the argument of a sine or a cosine, that does nothing because sine and cosine are periodic with period 2 pi. So that's the same as just the cosine of 2t. And then the same thing for the last term. It's 4e to the t minus pi times the sine of 2t. And there's our answer to that one. So if your initial t value, t is 0, if it's not 0, you can sometimes do a substitution like in this example to make a new initial value problem where t0 is 0 and then apply this method and then as a last step undo that substitution. Okay, we have one final example for this section. For this example, we're going to need to use two facts. The first one is one that we've seen already. I'm just copying it here. This is from Table 7.2, those properties of Laplace transforms. So this is just a reminder that the Laplace transform of t to the n times f of t is equal to negative 1 to the n times the nth derivative of capital F. The second fact we're going to need to use in this final example is this. If f is piecewise continuous and has exponential growth, then, well, we already know that it has a Laplace transform, but not only does it have a Laplace transform, the limit as s goes to infinity of that Laplace transform is equal to 0. So I'm not going to prove this fact. The book mentions that there's a sketch of a proof in the examples. In fact, or not the examples, I'm sorry, the exercises, or the exercises. Exercise 7.3.26 gives a sketch of a proof of this fact if you wanted to look at that. What you need to do to prove this is go back to Calc 1 and remember two things from Calc 1. Number one is the squeeze theorem, and number two is, I don't know what the name of it would have been in the course that you took for Calc 1, but it's one of the comparison theorems for the integral. Right, that the absolute value of an integral is less than, and we're talking about definite integrals here, the absolute value of a definite integral is less than or equal to the definite integral of the absolute value. So this is one of these comparison theorems that hopefully was covered when you took Calc 1. That and the squeeze theorem together could be used to prove this fact. So if you want to look at that yourself, that's a useful exercise to test your conceptual understanding of some of these properties. Okay, so we want to use those two in this last example. So here's the example. Now typically we're only doing examples where we have constant coefficients, but this example we've got variable coefficients. There's a 2t in front of the y prime. So there's my differential equation. My initial conditions are y of 0 equals y prime of 0, and both are equal to 0. Okay? All right, so again, I want to start off the same way. I take the Laplace transform of both sides. So I have the Laplace transform of y double prime. Using my property from before, that's s squared capital Y minus s little y of 0 minus little y prime of 0. Okay, plus So that's the Laplace transform of y double prime. Plus 2 times the Laplace transform, and do this one in a second step, of ty prime. Okay, minus 4 times capital Y is equal to the Laplace transform of 1, which is 1 over s. Now, y of 0 is 0, and y prime of 0 is 0 in this problem. So this gives me s squared y plus 2. Now I'm going to use that property of that first fact, if I scroll back up here, that first bulleted fact right there. So n is 1. So I've got negative capital Y prime. Well, not quite. Negative 1 times dds. It's not y prime. It's not capital Y prime. I misspoke. We have the negative 1. Let's scroll back up here. Okay. So here is the thing that we are looking at. We're applying this first bulleted rule to it. So n is 1. So there's where I get my negative 1. And then what I need is the first derivative of what? Well, it's going to be the first derivative of the Laplace transform of whatever is here. Well, in our example, what's there is y prime. So I need the first derivative of the Laplace transform of y prime. Okay, then I have minus 4 capital Y is equal to 1 over s. All right, now I have to keep going. So I have s squared times capital Y minus 2 times dds. Now I use my rule. What is the Laplace transform of little y prime? It's going to be s times capital Y of s minus little y of 0. Little y of 0 is 0 in this example. All right, now I've got a product. S times capital Y of s. I need the product rule here. So 1 times y plus s times capital Y prime. So I have s squared capital Y minus 2y minus 2s y prime minus 4y equals 1 over s. So minus 2s y prime plus s squared minus 6y equals 1 over s. And what I have here now is I have a first order linear differential equation for capital Y. My whole objective here is to find little y, and I do that by first finding capital Y and then taking the inverse Laplace transform. So I have to find capital Y, but instead of just an algebraic equation for capital Y, in this example I have a differential equation. So I have to solve this using the methods from chapter 2. So let's put it into standard form. Divide by negative 2s. So I have y prime minus s squared minus 6 over 2s times y equals negative 1 over 2s squared. All right, I have to figure out what my mu is. So going back to chapter 2, recalling all of that, mu is e to the integral of the coefficient there in front of y. So I have s squared minus 6 over 2s ds. So now we have to figure out that integral, pull out that minus sign, split up the fraction, got s over 2 minus 3 over s. So what do we have there? S squared over 4 minus 3 log s. All right, so that's going to be e to the negative s squared over 4 times e to the 3 log s. E to the 3 log s simplifies to s cubed. So my mu is s cubed e to the negative s squared over 4. Okay, we come back to our equation here, multiply the whole thing by mu. So I have s cubed e to the negative s squared over 4 times y prime minus s squared minus 6 over 2s times s cubed e to the negative s squared over 4 times y equals negative s over 2 times e to the negative s squared over 4. As it does in this method, the left-hand side simplifies to d ds of mu times y, so d ds of s cubed e to the negative s squared over 4 times y is equal to negative s over 2 e to the negative s squared over 4. Integrating both sides, we have s cubed e to the negative s squared over 4 times y is equal to negative 1/2. 2 didn't look very good there. Negative 1/2 times the integral of s e to the negative s squared over 4 ds. All right, to integrate that, I'm going to need a u substitution, so I will substitute u equals s squared over 4. Then du will be 1/2 s ds. Substituting that in, I get negative integral of e to the negative u du. So that's e to the negative u plus c. Plugging back in for u, we have e to the negative s squared over 4 plus c. Finally, solving for y, capital Y is 1 over s cubed e to the positive s squared over 4 times e to the negative s squared over 4 plus c. And we can simplify that by multiplying it out. I get 1 over s cubed plus c over s cubed e to the s squared over 4. Okay, let's take a breather and look at what we've got and try and not lose sight of our goal amidst all the details. Remember our goal, we started with an initial value problem. And so we were looking for a solution, not a general solution, a solution to the initial value problem, so that it's one function that we're looking for. And we're going to find it by first finding capital Y, then doing the inverse transform. So we're not looking for a family of functions. We're looking for one function, capital Y. It's not supposed to have an unknown constant in it. We need a value for that capital C. But how can we possibly get any value for that? There's nothing that we haven't used. We've used our initial conditions. There's nothing else in the givens of the problem. Well, the trick here is to use that second fact, which I said you had to use one of the exercises to prove. The fact that the Laplace transform goes to 0 as s goes to infinity. So, if I look at, let's say I subtract 1 over s cubed from both sides. So y minus 1 over s cubed is equal to c over s cubed e to the s squared over 4. Now both sides are the same, so they should have the same limit. Let's look at the left-hand side. The limit as s goes to infinity of y of s minus 1 over s cubed is equal to, the Laplace transform goes to 0, 1 over s cubed goes to 0, so that limit is 0. Well, what's the limit as s goes to infinity of the right-hand side? Well, we could work this out with all the details like you would in Calc 1 or Calc 2, wherever you do these. I guess it's Calc 1 where you would do the limit of this one. Maybe Calc 2. Not sure. It's been a while since I taught those. But we could go through the details, but let's not. Let's just think about it heuristically, assuming that you know the right heuristics for the growth rates of these functions. So in the denominator there, you've got a polynomial. So that's going to go to infinity at a polynomial rate. And in the numerator, you have this e to the s squared. You have this exponential. So that's going to infinity at an exponential rate. It's a much higher rate. And so the whole thing, as s goes to infinity, that part, if you ignore the c, or if you think that if c were 1, then that thing's going to infinity. But there is a c there. We can't ignore it. So this limit is going to depend on the value of c. It's going to be infinity if c is positive, just by that reasoning that we had there. If c is 0, then it doesn't matter what s you plug in. That thing is always 0, so the limit is 0 if c equals 0. And if c is negative, the rest of it's still going to infinity, but with that negative in front, it's going to go to negative infinity. Well, the two sides, the left and the right-hand side, have to have the same limit. So the right-hand side, the limit has to be 0. The only way for the limit to be 0 is if c is 0. These two limits are equal. So therefore, c is equal to 0, and I now know that y is 1 over s cubed. Okay, so I don't know why now I've got a big mess. Having writing problems here. Okay, y is 1 over s cubed. All right, so little y is the inverse Laplace transform of 1 over s cubed, which I can write as 1/2 times the inverse Laplace transform of 2 over s cubed, and 2 is equal to 2 factorial, and we can read that one off the table. That inverse Laplace transform is t squared, so 1/2 t squared. Okay, and that's it. That's it for this week. These two sections, 7.4 and 7.5. Oh, good timing too. Low battery. All right. We'll see you in the next video next week.